Hey guys, hello everyone and welcome to the channel. So since the CSIR NET has uploaded their answer key, there are so many questions on which you guys are asking that it should be challenged or the answer key isn't correct. The first question which I actually discussed was regarding this polymer question, and this was the most controversial question. A lot of you were asking about it. So I have already solved this question. The link is there in the I button. You can click on the I button and you can watch that video. It's a very small video, but I have explained how the answer is coming 40,000. Okay, it's not at all correct. Sorry, it's not at all incorrect in the answer key. It's actually a correct answer. Okay, so don't challenge this question. Similarly, in this video also, because after that so many other questions also you guys told, so I have only taken those questions on which most number of you have asked, okay, that whether the answer is incorrect or something. So I have taken those questions and I'm going to explain you. You guys might hate me for this, but I have to tell you that what exactly the answer is, and like you should know, right? It might happen that you might have done mistake in the exam, or you might not know that and you have made that mistake while solving the question. But now since the exam has happened, we have to learn also that what mistakes we have done. So keeping that in mind, I'm going to solve the other questions. So I'm going to take 3 questions which were most asked. Out of those 3, this was the most hyped question. So if I give you the ranking, so this was the most controversial one on which most of you were asking, ki sir, this is going to be challenged or something. This is not going to be challenged. Okay, this is correct in the answer key. The correct answer is 40,000. I have already solved. Second is about this question, question ID 745 regarding the phase equilibria. This also is a correct answer. Okay, the answer is given correct in the answer key. The question says that when 3 of the phase of 2 component system are simultaneously in equilibrium, the number of degrees of freedom is. Okay, so there the question is, or the confusion is, that we have to use reduced phase rule or the normal phase rule. Okay, so the phase formula or the phase rule according to Gibbs is F is equals to C minus P plus 2, right? And if you are using this phase rule, you are getting answer 1, right? There is nothing nothing to worry about it. So this is the normal phase rule which you have to use. So I'll first of all solve it. So since it is said that it's a 2 component system, and since there are 3 phases which are over here and plus 2 if you put, so you are going to get 1. 2 minus 3 is minus 1 and plus 2 is plus 1. So it is going to give you 1 as the answer, which is correct. Now many of you are asking that why are we using the normal phase rule? Why not we are using the reduced phase rule? See, it might happen, and that's what I always recommend to read books. Okay, that's where you are missing the point. So Gibbs gave this rule which is called the Gibbs phase rule. Okay, this is called Gibbs phase rule. Now there is one more rule which is called reduced phase rule, and that rule says that F is equals to C minus P plus 1. When you have to use this rule, okay, be very careful that when we are going to use this rule, and I'll not say it in that, I'll show you with the with some reference. So I'll just show you what's there on, if you just search about the reduced phase rule on Wikipedia also. Okay, so this is the page on Wikipedia regarding the phase rule. So if I come a little down over here, and if I talk about the 2 component system, you can read about it. Okay, the text is small on the screen right now. It says for the binary mixture, 2 component chemically independent component, C becomes 2, then F becomes 4 minus P, and if you are using this formula, that is coming from the normal formula. So 4 minus P, in the given question phases are 3, so 4 minus 3 is coming 1. Now what happens when you use the reduced phase rule? That's given over here. Okay, so it says that phase rule at constant pressure. Now it says for application in the material sciences dealing with the phase changes between different solid structure, pressure is often imagined to be constant. Okay, for example at 1 atmosphere, and is ignored as the degree of freedom. So the rule becomes F is equals to C minus P plus 1. So this reduced or condensed phase rule, okay, this is called, as it says, right, this is sometimes misleadingly called condensed phase rule, but it is not applicable to the condensed system which are the subject to the high pressure, since the effect of this pressure can be important. Fine. So what they are telling over here, that this is actually your reduced phase rule, and this reduced phase rule is used in those components where pressure is kept constant. Okay, is kept constant. Or usually you have studied this in the 2 component systems. Let's say you have studied in lead iodide system, a lead iodine system, right, or any of the system which you have studied in your books, those are generally solid systems. They are not converting into the gaseous form, or they are being done at the constant pressure. That's why in most of the derivation or general notes which we make for reduced phase rule, we use the formula F is equals to C minus P plus 1, because we keep pressure constant over there. So when pressure is kept constant, then only this rule is going to be used. In the question, there is nothing mentioned about it. Okay, they are not telling that you have to do it at constant pressure, or they are not telling you to do it at certain condition. Okay, they are just telling that when the three of the phases of two component systems are simultaneously in equilibrium, number of degrees of freedom are what. Okay, so if you have studied Gibbs phase rule properly, you would have known this, and the answer would have been 1. If you would have put extra effort to solve it, you would have done it in this way, and in that way your answer would be coming 0. That is an incorrect question. So I don't think that this question needs to be challenged. Reduced phase rule is only applicable. See, reduced phase rule is nothing which Gibbs gave. Okay, Gibbs didn't give, or it's nothing official if officially given by Gibbs. Reduced phase rule is something which is derived from the phase rule, from the normal phase rule. See, I'll tell you one thing first of all, that what exactly this degree of freedom tells you. Degree of freedom tells you that how many variables you need to explain the system, or to express the system. So in your one component system, you need at least 2 things to express the system, like starting from temperature and pressure. Then you go for either only pressure, that means if you need temperature and pressure both, that is called like degree of freedom becomes 2 over there. Then when you say, let's say if this is your degree of freedom, so here in the areas you get degree of freedom F is equals to 2, right, whereas on the lines or on the curves you get F is equals to 1, because you just need one variable to express the system on this line, whereas on this point, which is the triple point, you need like 0 degrees of freedom. You don't need any variable to express the system over here. That's why it comes 0. But in the 2 component system, you have 3 variables over there. What are those 3 variables? Those are like temperature, pressure, and the third variable over there is component. Component means mole fraction. That's why wherever you might have seen the 2 component system, it starts from A, B, and it goes something like this, right? You get a eutectic point, and in this case A is, let's say, 0%, here A is 100%, and so on. So the third component over here comes is the third variable which comes is mole fraction. So temperature, pressure, and mole fraction, 3 things are there. Now since you are suppressing the pressure, or you are not using the pressure, so one variable is reduced, and that's why the formula becomes F is equals to C minus P plus 1, because you are not using one of the variable in that condition, keeping pressure as constant. I hope you understood, and this is something which is taught at very basics of phase equilibrium, and every one of you should know this, right? But in case, I know, see, that happens, and you might got carried away with the formula which you might have heard or might have studied in your notes. So that's why you might be thinking, okay, option A is correct, but it's not. Okay, option B is correct. That is 1 should be the answer for this particular question, and I don't think this question needs to be challenged. If you want to discuss on this, you can discuss in the comment section below. All right. Okay, so this is the first question, and this was highly asked or highly requested one. The second question over here is the major product formed in the following reaction is. Now this is a reaction where your allene is reacting with your it's a reaction, cycloaddition reaction in the presence of heat. Now you are asking what is the product or what is the answer for this. Many of you are telling that it should not be 3098, but it should be 3099. Right, so that's what is the question. I'll tell you with a reference to this. This is also a correct option. Okay, this is also given correctly in the answer key, and I have a reference for that. See, in the presence of heat, this undergoes 2,2 cycloaddition. I'll give you the reference and then I will talk about. So this is, I'm giving a reference of a research paper. I will give you link to download the research paper also in the description of this video. So this is the research paper which says exploiting 2+2 cycloaddition chemistry achievement by, with allenes. Okay, so this is a research paper which was published, I guess, in 2010, right? So 2010 it is published. Let's come down to the part where we have to actually look upon. So coming down a little bit, exact same reaction is given, right? I'll zoom this up a little bit so you can see exactly same reaction is given, and on reacting you are getting 2 product number 8 and product number 9, and if you see the ratio over here, if you see the ratio, so the the product 8, which is this, is 11.5 times more than product 9. So the ratio is given 11.5:1. That means this is 11.5 times more formed than this, and 27% is the yield. Okay, that's the yield which you are getting. You can read the text also over here. It says that on the other hand, considerable attention has been devoted to study the cycloaddition reaction of allenes with alkenes and alkynes. For example, 2,2 cycloaddition of 1,1-dimethylene in dimethyl fumarate as afforded 2 cycloadducts 8 and 9. Okay, so 8 and 9 are the 2 cycloadducts we are getting in a 11:5:1 ratio. So that means 8 is the major product, 9 is the minor product, okay, in which more than 99% stereochemistry is claimed, the reaction is optically active, and all the other things are given to you. But what you have to understand is that this particular whole thing is the paper itself, or the research paper itself, titles exploiting 2+2 cycloaddition of cycloaddition chemistry. So the reaction is over here in scheme number 7, which is 2+2 cycloaddition of 1,1-dimethylallene with dimethyl fumarate. Reagents and conditions are given to you. So the reagent is nothing but just temperature. Okay, just heat is given, 160 to 180 degrees Celsius. Time is around 18 to 70 hours. So this clears up that this is the major product, and that's what is shown in the answer key as well. Okay, so this is the major product. So I'm not that great with organic chemistry, but still I found a reference for you so that you get settled with it, that yes, this is the correct answer. Okay, I hope you understood. Those who are good at organic chemistry, they might understand it in much a better way, or they might be able to explain you this reaction in much better way. I'll give you link to download this research paper. Okay, I understand that you might not have access to download this. Okay, I'll download the research paper and I'll give you the link to read it. Okay, that I can do, right? So next question. So this was question ID 775. The last question for this class is question ID 754. Again somebody asked me ki sir, the type of molecular orbital in the allyl ligand. Okay, allyl ligand, that is CH2CH, CH2 minus, that are used for sigma donation and pi back donation with the metal d orbital respectively are. The answer which is given in the answer key is 3014, and this is again a correct answer. Okay, so it should not be challenged. This is again the correct answer given in the answer key. Let me show you with the reference again. Okay, so you have to look upon the molecular orbital diagram of this. Okay, how allylic ligand interacts with the metal. So for that I have a reference over here somewhere. Yeah, so molecular orbital of the allyl cation, allyl radical, and allyl anion. I'll give you a link for this particular website. You can directly go to this. It's a very well known organic chemistry website, masterorganicchemistry.com. and many organic chemists know already about it, but fine. What I am going to show you and what we are going to focus on is full molecular orbital diagram of allyl system as formed through the interaction of pi bond with the p orbital. So these are the pi bond, these are the p orbitals. So atomic p orbital here shown empty, but can be singly or doubly occupied, and these are molecular orbital from the forming the pi bond. Okay, now you will see that they interact in this way and they form 3 orbitals. They form, let's say, orbital like pi 1, pi 2 and pi 3. These will be the 3 orbitals which are going to be formed, where this pi 1 or psi 1 is, this is mentioned in the form of psi 1, but in the question they have mentioned in the form of like 2 pi, 3 pi, 1 pi, right? So this is nothing but 1 pi means the first pi orbital, 2 pi means the second pi orbital, 3 pi means the third pi orbital. Okay, that's what it means. So here again you can see, because these are pi orbitals only interacting with it, so although it is mentioned as psi 1, psi 2, psi 3, but this has to be considered as, you can consider according to the question as pi 1, pi 2 and pi 3, or 1 pi, 2 pi, 3 pi. We will see that this one is going to be used in the bonding, okay, or this one will be used in the sigma bonding. Which orbital? This is basically your 1 pi, right? So 1 pi will be used in sigma donation. Okay, so 1 pi used for that, and for pi back donation, you know that back donation is done in the anti-bonding orbital. So this anti-bonding orbital is going to accept the electrons from the metal, and this is going to be the one which is going to behave, or it's going to be used in the anti-bonding characteristic. So pi back donation is going to be done in 3 pi, and that's why the answer given is 1 pi 3 pi, and option ID is 3014, right? So this is again a correct option given over. So as of now, I didn't found any question which is incorrect. Organic chemistry questions, I'm not that great with organic chemistry, so I won't be able to evaluate them much. Physical chemistry questions, whatever you guys have suggested, I tried to search it out, but nothing mistake no mistake I found in them, and most of them seems to be correct itself. And apart from all these, one more very important thing, that I'm going to take a live class on Unacademy where we are going to discuss these questions. So in case if you have more questions and want to discuss them up, you can join me at Unacademy. The timing for the class is 1:30 p.m. today. Okay, so the link to join the class, this is a live class by the way. Okay, so I'll be there during my lunch time, so I'm going to spend my lunch time with you guys. So you can come and live to this class, join me over there and discuss out questions. The link to the class is there in the description of this video. Okay, so use that link to enroll yourself into the class, discuss out the questions which you have, and in that way we will be able to interact more and we will be able to discuss more questions, right? So that's it from my side for this particular video. I hope you guys understood. I hope the references and the explanation made sense to you, and thank you so much for watching. I'll see you guys in the next one. Till then, have a great day. Bye bye, take care.